Well, that was awesome. Let's give our collegiates another thank you. That was so helpful to learn how we are evangelizing in the universities. Now, we have a special panel here, workshop coming up. We have Dr. Bernhard Scholz, Chief Research Officer for Sonic Labs. And he's going to be leading 3 workshops that I'll allow him to introduce because it's a little over my head, but this should be extremely informative, and I personally am really looking forward to it. So, again, let's say welcome to Dr. Bernhard Scholz.
Hi there. Today I would like to talk about Sonic's technology. So I apologize ahead of time that it might be very technical, the talk. So it might be a little bit different to other talks. And I will not talk just on my own. 2 of my team members, Paul and Camille, will talk as well, more specifically about consensus and the database work. But let's start just with Sonic's technology. I want to give you an overview what we did the last 3 years, and it was a tremendous effort, I can tell you. It was not just an effort in terms of building the technology, it was also an effort building the teams that produced the product Sonic. And so it was really a very busy time for us doing this. But before we started, we really thought about the requirements, what Sonic should do. And one of these requirements was sub-second time to finality. So we really wanted to have a very fast blockchain. And this goes back to, user experience studies that we really want to have transaction times which are below 1 second so that the user have very smooth experience. The other thing what we wanted was 100 million transactions per day. This was a little bit taken from thin air, but we thought America has roughly 100 million transactions per day. Credit card transactions, and we thought that's a good benchmark for us as well. Other requirements came from the actual maintenance of validators from the Phantom network. And here we noticed that the state DB, which stores accounts, balances, and so on, gets very bloated, and we wanted to have a more efficient way of storing this data, so we wanted really to bring the storage consumption of the StateDB down. And other things on the list were we wanted to be EVM compatible. We wanted to ensure that the adoption of Sonic should be very easy. People can just transfer their apps from the Ethereum ecosystem to us. Other things on the list were easy maintenance for validators. In the old days, we had a little bit of issues there. We wanted to have a really smooth experience for running nodes in the network. And the last point came a little bit later. It was about making sure that people can transfer their assets from Ethereum, from Phantom to Sonic. So we built bridges, which took also a lot of effort. Overall, again, it was an effort of 2 to 3 years, and it was substantial from a technological viewpoint, but also from rebuilding the technical arm of Sonic. I just want to give you now an overview of the client, and I want to stress building clients is very complex. It touches a lot of areas in computer science. It goes from database design, from databases to programming languages, to distributed systems, to performance engineering, to systems engineering, to software engineering. So nearly all topics, including cryptography, I forgot, nearly all topics of computer science are touched, writing clients. And writing fast clients means that all of these different components in the client need to work very nicely together. So they need to be perfectly balanced to get performance. So you need to really ensure that they have a nice equilibrium in terms of performance, and just, for example, optimizing the virtual machine doesn't guarantee you that you have a fast network. So if we talk a little bit more about the client, so we have here two major components. So we have the block processing and the distributed system components. The block processing is there to really perform these transactions. So they do a state transition in the state DB where the virtual machine executes the smart contracts. And there needs a lot of technology if you want to make it fast. So you need to have a really fast language implementation, in our case, the Ethereum virtual machine, and you need a fast database to really achieve the speeds we are seeing in Sonic. But it's not a block processing on its own. There are other components in a client, in that case, the distributed system components. We have CS, that stands for consensus. We have a peer-to-peer network with all its complexities, transaction pools, and then something called RPC, which then interacts with all the web applications. So a lot of components are in a client, and it's a highly complex endeavor to build a client which has the performance which we see in Sonic. So now the question is, what is the technical innovation in Sonic? We are very proud of three major components. One is the Sonic DB. It's really a radical new solution to state DBs we find in the Ethereum ecosystem. It's a high-performance native blockchain database. What it means is we don't rely on other databases like LevelDB, RockDB, and so on to store the information. We have built a native database which is super fast and is really one of the crown jewels of Sonic. The other high-performance component is the virtual machine, the Sonic VM. It's a high-performance virtual machine, so with our background in programming languages, we could use the best techniques in terms of speed, but also in terms of getting the right balance between software engineering time and the performance. Not last, it's the Sonic consensus. This is not currently in the current release 2.0, but will come soon. Paul will talk more about the Sonic protocol later, and he will give you a deep dive into the new consensus, which will then further improve Sonic in this year. But there are many other things, and this I really want to stress. I mean, besides these major innovations, a lot of components needed to be touched in the old Go Opera client to make this really work fast. So we had many changes in the transaction pool. We had many changes related to the event emission, RPC interfaces, and other components. And I want to stress, Sonic is EVM compatible. We had a lot of effort really ensuring this compatibility. We needed conformance testing, very strong testing infrastructures to really show that these implementations are compatible. Currently, release 2.0 is compatible to Takun, and soon to come in the next few months, we will have release 2.1, which is compatible with Pectra. And Pectra is important for the app chain. I will have a few slides on this later, but we have this lined up, and that will be a big leg up for the D-apps so that they can implement account abstractions, gas subsidies, dynamic gas, and so on. So let's talk a little bit more about Sonic DB. I mean, again, Kamil will talk more about this, but let's talk why it's so fast. Why could we achieve the speeds we are seeing on Sonic? And here, this is sort of something very natural. What you have to do when you do performance engineering, you need to split the task into special cases. And what we did here is we implemented two different types of databases. One type of the database is for validators, which do not keep track of the historical states. They just keep the current state of the current block and move on. And the other type of database is, we call it ArchiveDB, and they are really there for the archive nodes, keeping track of historical states and blocks. And they have two fundamentally different tasks, and therefore we came up with two different designs and split the responsibility between these two databases. With that, we can really then implement automated pruning very efficiently. So these data structures use Merkle-Badrischer tries, and they are not really efficient. But with very special indices, we could then build very fast pruning, fast synchronization, and at the end, we got high performance. So Sonic DB is, again, one of the crown jewels of Sonic and is a major contributor to the performance we are seeing. Let's talk a little bit more about Sonic VM. It's also a complete new implementation of the Ethereum virtual machine. We put a lot of effort into compatibility, so we extracted a semantic specification from Go Ethereum, and with that we cross-test our virtual machine to really ensure, with fuzzing, to ensure that we are fully compatible. Again, today we are compatible with Darkoon, the latest Ethereum, but soon we will have Bactra in the next few months. How it works, the virtual machine, is via dynamic translation. So what this means is that the actual virtual machine encoding of the Ethereum virtual machine is not very fast when you implement it. So we came up with a new type of encoding. We call it the long format virtual machine encoding. And with that, we get really good speeds. It uses, if for technical people, we use some tricks to avoid jump test analysis. These are sort of analyses which need to be executed every time when you run a smart contract, and that really slows you down. And we have some very good tricks to avoid the analysis again and again. And then also we have tricks to cache cryptographic hashes so that we have here sufficient speed for Sonic. Overall, here is sort of a conceptual diagram how this works. So we have a just-in-time compilation of the EVM virtual machine to this long format virtual machine code. We have a converter. We have a cache for these conversions, so we don't do it every time again and again when this new smart contract is executed. And with this new format, we can then execute smart contracts very fast. We see this in the block processing performance. So this is a small little experiment, performance of block processing in isolation. What we see is that Sonic has a gas rate of, can process about 1.3 gigagas per second. There's a very recent version of Go Ethereum can go only up to 210 megagas per second. You see here really big differences in speed. Older versions of Go Ethereum were even slower. Besides the block processing, we have other components, and again, we are very proud of the Sonic consensus component. Here, what we have is a DAG-based consensus protocol. It's a whole family of consensus protocols where a global data structure is shared between the validators, the DAG. If you're mathematically inclined, it's a partial order. And this partial order is synchronized between these validators, and then synchronization points are detected in the data structure. And then with these synchronization points, total order is formed, a chain, you can say. And from that chain, we then build the blocks. This new consensus protocol, and Paul will talk in much depth about this new consensus protocol, has really good new features. It overlaps these defining of the synchronization points. We call this elections. So the overlapping these elections brings us a lot of speed and also reduces space. We can express this in a matrix calculus, and it's quite exciting seeing new innovation in the consensus space for Sonic. So overall, the mainnet is really doing very well. Michael presented some numbers today in the morning. So we have now up to 24 million blocks as we speak. On some days, we reach 1.4 million transactions. So we are way below the specified 100 million transactions we wanted in terms of capabilities of processing. In our experiments, we are way above the 100 million transactions per day. So our Sonic technology can do much more than 100 million transactions per day. But this is what we aimed for. And so, you can run so many more DApps to really saturate the supply we have still. We see already very large blocks occasionally with 1,000 to 2,000 transactions. And again, we see really that we have this sub-second time to finality. And as a really nice side effect of all this technology, we have very low costs of running the validators. So that's really nice and helps us a lot. Besides the Sonic client technology, we had to also invest in building bridges. So this is really we call it the Sonic Gateway, which builds a bridge between the Ethereum and Sonic. It's a fully decentralized bridge, and you can ship across your tokens, ERC20 tokens. It's sort of quite unique in the space because we have something called the fail-safe mechanism, and many other bridges don't have this. So what it means is that if Sonic or the bridge go down, then the end users still can recover their funds. Bridges are very complex, so you have here a closed world assumption of tokens, so you can't just ship tokens directly from one blockchain to the other, so you need to lock tokens on the sender blockchain. Then they need to be other corresponding tokens need to be minted on the receiver blockchain, and it's quite a complex process, and getting this right is hard. So we had 3 auditors checking for the correctness, but we even went beyond, and we built mathematical proofs, formal models, describing the operations of the bridge and showing that users can never lose their money, because in case something goes wrong, the tokens will be unlocked. We can see, if you look up at L2B, it's quite substantial token value already on the bridge. That may change because of the USD's launch. The native token will come soon, but you can see it's already above 1 billion on that Sonic Gateway. So this is quite impressive in this short period of time. So I want to talk quickly about the methods we use to really make this fast. So one of our key methods is performance engineering. So what this means is it's sort of a flywheel we do in the design of new technology. So we have a prototype, we test it functionally, but then we have an evaluation. We check whether the performance is sufficient, and if it's sufficient, we are happy, but if not, we analyze the bottlenecks and we do the whole process again and again till we have a satisfying solution. We have a lot of infrastructure in the client space for performance engineering. This took a lot of effort building this, so we have for block processing, we have a project called Substates, which run transactions in full isolation to really check on a single transaction where the performance bottlenecks, but we have other systems like Project Norma, which runs a whole network on a single node with Docker or test nets. So we have really a lot of infrastructure to check the performance and the functionality of our client. Beside this, we use the most modern techniques in software engineering. We do a lot of testing, unit testing, regression testing, system tests, coverage, continuous integration, and all this. But recently, we really stepped up and tried to formalize a lot of these testing strategies with mathematical models. So I'm running a little bit out of time, so I want to speed up here. We have now the question, why was it so a success? Besides the technology and the testing and whatever we do, we hired very strong people from big tech, which helped building this team. And we favored long-term perspectives rather than short solutions quickly, and we build on core principles. So what I want to say in the last few minutes, there is now a big paradigm shift on our chain. We want to have now this developer-first approach. It produces a continuous revenue stream for DApps, and the idea here is that we support DApps in terms of fee monetization. There will be some talks about this, but also with the new Pectra upgrade in release 2.1, we have the ability to for gas subsidies and dynamic gases. Okay, so the last slide I want to talk today is what's going on beyond Sonic. So at the moment we are in the planning for what should come after Sonic. So at the moment we seek from the community requirements, so to plan for the technology which hopefully will be deployed in 2 years or 3 years' time. We know we have this development time of these 2 to 3 years for a new technology, and ideas would be like 10 billion transactions per day, so it's like all credit card transactions in the world have roughly 2 billion, but also scaling decentralization, scaling apps, which type of language should be used, like RISC-V, EVM, Move, and so again, our time horizon will be 2 to 3 years. So if you have any feedback for us, we would greatly appreciate this. Thanks so much for your attention, and questions, please. Yes?
Okay. Sorry. Well, one of the hallmarks of the Phantom ApronNet was its robustness, which sort of went unmentioned. It was taken for granted. But what I want to know is whether Sonic's chain will be as robust as, say, Phantom's.
Well, as you know, the Phantom client was the building block for Sonic. So the actual client architecture is still the old Go Opera architecture, but we swapped a lot of these components out. So a lot of the building, the architecture from Go Opera is still there in the new Sonic client.
I have a simple, easy question, but I just want to hear, this is the assistant, by the way, so I'm on the Sonic team, but my question is for you is like, how does it feel to have built the fastest layer 1 EVM chain ever? Like, it's a huge accomplishment. I feel like underplay it, but the reality of it is that like Bernhard has put together one of the best teams in the world, and like you don't really see them that much, but we're fortunate to have 3 of them here today. And like I can't express like how thankful the Sonic team is on the BD side, the marketing side, the leadership side of like all of the hard work and innovation that they've put in for the past 3 years. I can confidently say that there are other chains that are shivering in their boots, having raised massive amounts of money, and we've accomplished not only what they're trying to achieve, but we've accomplished it at a fraction of the cost by just having Bernhard leading the team and running like the most efficient tech team, I think, in blockchain. So I'm curious, like, how does it feel to be behind and powering this great team?
Well, I'm first of all, I'm very grateful towards my team. So on my own, I could not have built it. It was really a massive team effort. And I'm very proud of my team that we achieved what we achieved. And it's a very long process. So you don't really realize at the beginning how much work is involved. So I'm really amazed that we are where we are. But if you have asked me this kind of question 3 years ago, I may have said something different. Any other questions? Okay, if not, then maybe we hand over to Paul. So maybe you want to give him applause to welcome Paul.